So in this video, what we're going to do is look at equilibrium constants and some of the valuable information that we can get uh, about an equilibrium constant is telling us something about what the expression is. And again, looking at how do we write out an equilibrium constant and our equilibrium constant values. What do they mean? If they are less than one, close to one, or greater than one, how does that tell us something about a reaction and the relative amounts of reactants and products at equilibrium? And then we're also going to look at how do we calculate equilibrium concentrations from information that we have provided about a reaction. We're going to be using this example reaction here where the equilibrium constant value is 1.1 times 10 to the negative fourth at 200 Kelvin. So we have bromine gas reacting with chlorine gas to give us BrCl. We could write out our Kc expression, reminding us it's always products raised to the power of their coefficient. So this would be 1, 2 for BrCl, and then divided by our reactants Br2, Cl2, each raised to the coefficient of 1. And so that would be our expression there. And we know that the ratio of those products to reactants is 1.11 times 10 to the negative fourth at 200 Kelvin. So if we think, what does this number tell us about our reaction? And we can answer this question number one saying, at equilibrium, what side of the reaction is favored? And favored, we mean it's more concentrated or has a higher concentration at equilibrium. Okay, and again, this is looking at our equilibrium constant tells us something at equilibrium. So again, reminding us dynamic equilibrium, the concentration of our reactants and products are constant. In addition to that, we would see that we still have our reactions occurring. But what does this equilibrium constant ratio, specifically our equilibrium constant value, tell us? So what we see here is that our Kc value is 1.11 times 10 to the negative fourth. We could also write that maybe in a decimal form and just saying that's 0.000111. And this, what we see is a very small numerical value. It is much, much, much less than 1. So it's really small. We're not going to see negative Kc values because remember it's a ratio of our product and reactant concentrations. We could see really large or we could see really small values for our Kc. And what this tells us is that at equilibrium, the concentration of our reactants is much greater than the concentration of our products. And we can make that conclusion because this ratio of products to reactants is very, very small. Again, reminding you that this is the ratio of products over reactant concentrations at equilibrium. So this would tell us that our reactants are favored here. We have a much higher concentration of our reactants at equilibrium than we would observe for our products. So that's kind of a generic thing that we can observe when we're looking at our Kc value, talking about whether it's a very large number or very small number. That would tell us something about our equilibrium concentrations for our reactants and products. In addition to that, if we look at our second question here, what other information can we pull out about equilibrium constant? Here we have this reaction, and we wanted to calculate the equilibrium constant value for that reaction at 200 Kelvin. And what we see here is that if we were to connect these two reactions, what we notice is that these two reactions are actually opposite of each other or reverse of each other, right? Because if we were to write out our equilibrium constant expression, it would be our products, chlorine gas, bromine gas, divided by our BrCl squared. And what we notice is that is the inverse of our original expression. So if I already know what that ratio is of the original expression, 1.11 times 10 to the negative fourth, what we see here is that the Kc of this reaction is going to be the inverse of that. So 1 over 1.11 times 10 to the negative fourth. And the reason why we would say it's the inverse, and that is because we have flipped what our reactants and products are. We've made BrCl wasn't originally a reactant, now it's a product. Br2, Cl2 were originally reactants, now they're products. So the ratio that we would observe should be the opposite ratio, or the inverse of that ratio. And here what we'd see that this would be, should be a very large number, which in this case is 9.01 times 10 to the third. And again, we should make the same observation. If bromine and chlorine at equilibrium have the higher concentrations, then we should also see chlorine and bromine at equilibrium having the higher concentrations. We're looking at the same reaction. All we've done is looked at it through a different lens. All we've done is flipped out what our reactants and products are. But it's the same reactants, same products. All we've done is flipped what our reactants and products are. And so we should see that we would be able to pull out some information just like we would here. In this case, we would say our products are favored because this is a large value, much greater than 1, and that would tell us that our products, Cl2, Br2, are favored, or they would have higher equilibrium concentrations once we've reached equilibrium. Okay, so we can see that all we've done is reverse this, and we notice that the Kc value is now the inverse of that because we flipped what our reactants and products are. Now the next thing we want to think about is, well, we looked at it a different lens, we flipped what our reactants and products are. What happens, question 3, when we start with different initial amounts? So experiment A, we start with 0.15 molarity Cl2, 0.25 molarity Br2. We put it into a 5-liter reaction vessel. Circumstance B, or experiment B, we start with the same amount of bromine and chlorine, but now we also start with some amount of that product there of our original reaction, 0.100 molarity BrCl. And we put it into a 5-liter reaction vessel. So what we notice here, we're looking at the same reaction. So why don't you go ahead and pause the video and answer this question here. Which of these following statements is true? The Kc value in reaction experiment A is larger than it is for B, smaller than it is for B, or equal to what it would be in B. So pause the video and answer which statement you believe is true. Now maybe as you had a chance to think about this, what you want to think about is what affects our Kc value? What are some variables there? And we see here that our Kc value is the ratio of our products and reactant concentrations at equilibrium. So we notice here that this is not saying that we have different concentrations at equilibrium. All this is saying, what we've done is we've started with different amounts. And so because of that, this is not going to affect the equilibrium ratio. This equilibrium ratio is a characteristic or property of the specific reaction. So not what our reactants and what our products are. And so what that would mean, because I still have the same reaction happening, that this would be where the Kc value would be equal to in those two circumstances. Because we've not changed the identity of our reaction, all we've done is change what our initial amounts are. Now that may affect what our equilibrium values would be, so what our actual concentrations would be, but we would see we are going to have the same ratio, that 1.11 times 10 to the negative fourth molarity, or sorry, 1.11 times 10 to the negative fourth would be our Kc value. Whether we start with one amount and start with a different amount. So what we're going to do is we're now going to apply this, and let's see, we're going to solve these two circumstances. Let's figure out, if I start with this much of Cl2 and this much Br2, how might that compare to the equilibrium concentrations that we observed in experiment B? So let's answer that first by looking at experiment A. So we're going to look at experiment A now. Again, initially a reaction container contained that much Cl2, 0.15 molarity Cl2, 0.25 molarity Br2 at 200 Kelvin. Now again, we think, what does this temperature tell us? That tells us we can use the same Kc value. Our temperature may affect or will affect our equilibrium constant. And so if we're dealing with the same temperature, we can always use that same Kc value. What we want to do now is calculate the equilibrium concentrations of all the reactants and products. So what is the equilibrium concentration of Br2, Cl2, and BrCl at equilibrium? So the best way that we have to kind of structure our thoughts as we're looking at these concentrations is setting up a Rice table. So remember, this is reaction, initial concentration, change in concentration, and equilibrium concentration. So again, we're looking at those different variables, and I'm going to designate a separation between my reactants and products with a double line just to help clarify it for us. So initially, we started with 0.25 molarity of Br2, 0.15 molarity of Cl2, and we didn't say we added in any BrCl, so then say, well, we start with 0. We didn't put any in initially. Well, now to go from our initial amount to our equilibrium concentrations, we're going to see that they're going to change by some amount. And this is what we're going to do, is we're going to use just some algebra, and we're going to say, based upon our balanced equation, our 1:1 to 2 mole ratio, these are going to have to decrease by some amount, and those would be equal because the mole ratio between Br2 and Cl2 is equal. But then that's going to give us twice as much BrCl as the amount that we get rid of for Br2 or Cl2. And again, we're just using those balanced chemical equations, the coefficients there. Now, once we've done that, what we'll see is that now, if we add these two up, what our initial is and then how much it changes by, that's going to be our equilibrium concentration expression for each one of these different variables. So now we have some expression, and what this becomes is the fact that what we need to do is we need to calculate what our change is. So we need to calculate what X is. How much are they going to increase by, or how much are they going to decrease by? And just to kind of take a step back, we said this is positive and these two are negative, because if we start with 0, the only way we can go is up or increase in concentration. So it has to increase by some amount, and then therefore by default, whatever's on the other side of our reaction, these need to decrease in concentration. Okay, we may see this might be the same or a little bit different from our second circumstance, which is looking at our reaction where we start with some amount of every single one of our reactants and products. So again, now we go back to the fact that we need to figure out what X is. For us to do that, we're going to first write out our Kc expression. And this helps us see the ratio of our products to reactants when we're looking at this reaction. So it's our Br2 BrCl squared, Br2 Cl2 on the bottom of our ratio here. And we know that that is equal to 1.11 times 10 to the negative fourth. Well, now we have some expression for each one of these. So we're going to go ahead and plug that in for our equilibrium concentrations. So our BrCl was 2x. I'm going to square that. Our Br concentration was 0.250 minus x. Our Cl2 concentration was 0.150 minus x. And then that's going to all equal this same ratio, 1.11 times 10 to the negative fourth. So now this becomes just, let's do algebra and solve for our x value. The important thing is that we can go from our original setup here to our Kc expression and then plug in our numbers there. The rest of this becomes some algebra. And I'm just going to go through this algebra very quickly. So we would have 4x squared would be our 2x quantity squared. And then we're going to have that divided by the values that we would have here for, we just kind of multiply those through and distribute. And we would get 0.0375 minus 0.4x plus x squared. And then that's going to all equal our 1.11 times 10 to the negative fourth. Now we got to continue to get a little bit more further here in our math. And so we'll see the next step is that we got to isolate all these to one side. So I'm going to multiply all of this across over there. And so we're going to get 4x squared equals our 1.11 times 10 to the negative fourth x squared minus 4.44 times 10 to the negative fifth x plus 4.16 times 10 to the negative sixth. And now I got to bring our x squareds together so we have like terms joined. And so we're going to get 0 equals negative 3.999 x squared minus our 4.44 times 10 to the negative 5th x plus 4.16 times 10 to the negative 6th. Now, if we wanted to, we can plug this into the quadratic equation. This is not an algebra class. My focus here is that we can set this up and then let a computer do what it needs to do to solve this for us, because it's just going to repeat over the same calculation multiple times. But what we do know is that this is going to pop out through some quadratic solver two different x values. So we get negative 0.00103, or x is 0.00101. And we think, okay, which one, do both of these make sense? Do only one of them make sense? And for us to analyze that, what we want to do is we want to take these numbers and let's go back and see, well, what if we plugged them back in here for our expressions? Well, right off the bat, what we would notice is that if we plug that negative value into our 2x, we will get a negative concentration. So this right here we can throw out and say that is not a valid answer, and that is because that gives a negative BrCl concentration. So we say, well, that x value doesn't make sense. The other one should hopefully make sense. It should give us positive concentrations for all of our reactants and products. So now that we figured out this change, what we're going to do is we're going to take that and plug it back into our equilibrium concentration expressions that we set up for Br2, Cl2, and BrCl. So let's do that. So we would say our Cl2 concentration was 0.150 minus x. So we'd have 0.150 minus 0.00101, and so we would get 0.149 molarity. Okay, so that would be our equilibrium concentration of Cl2. Can do the same thing for Br2, 0.250 minus x, so 0.250 minus 0.00101, and so we would get 0.249 molarity for our Br2 concentration, and then our BrCl was 2 times x, so it's going to be 2 times 0.00101, and so we get a concentration of 0.00202, or we could also, if we want to write it, 2.02 times 10 to the negative 3 molarity. So now we have our concentrations for each of our reactants and products at equilibrium. And what we could do is if we wanted to make sure that we feel comfortable with this answer and say those are correct, we could plug it back into our Kc value, our Kc expression. So that would be our BrCl concentration squared divided by our concentration of Br2 and Cl2. And if we did this, we should see that this should be pretty close or to the same number as our original Kc value that we had used to calculate this. And what we'd find is that this would be 1.10 times 10 to the negative 4th, pretty close to our original 1.11. And so that lets us know, based upon maybe the uncertainty of our measurements, okay, yeah, we feel comfortable these answers would make sense for our equilibrium concentrations of Br2, Cl2, and BrCl. In addition to that, we also said that we should have a lot more of our reactants, Cl2 and Br2, at equilibrium, which is what we notice. We have concentrations of 0.149, 0.249 versus 0.002 for our BrCl concentration. So we see here the main tactic that we use is we set up some kind of table that tells us what our initial concentrations are, how much they change by, and then the expression that we would have for each of those. Once we do that, then we go ahead and plug it into our Kc expression and then do some algebra to solve for our final answer. So now we've calculated the equilibrium concentrations of Cl2, Br2, and BrCl. And that was starting with reactant amounts. So now let's maybe shift gears a little bit and let's see how different is it if we start with some amount of Cl2, some amount of Br2, and some amount of BrCl. And so when we do this, it's going to be the same kind of process that we just followed. We're going to set up a Rice table. So reaction, initial concentration, change in concentration, equilibrium concentration. And so for each of these, we would say, well, we start with 0.25 molarity of Br2, 0.15 molarity of Cl2, and now we're starting with 0.1 molarity BrCl. So we actually put some of that into our container originally. Well, here we maybe come up to a little bit of a conundrum. Do we make this positive 2x minus x, or do we make this minus 2x positive x, positive x? Because again, it can go either way now. We start with some amount of each one of these reactants or products. And so for us to do that, we could just guess, and at the end of the day, the x value that we calculate will tell us whether that's right or wrong. So for example, if I choose incorrectly, the x value, the change that I calculate that makes sense, is actually going to be negative, a negative value. And that would tell me I assigned what increased wrong and I assigned what decreased wrong. Well, maybe to just take some conceptual ideas that we've been talking about and apply it here. So again, our Kc value is very small. And what that means is at equilibrium, we should see more reactants, specifically our Cl2, Br2, and less, and this is pretty small, much less of our products, BrCl. And so we look at that and we'd say, oh, well, then it probably makes sense for us not to say our reactant concentrations are going to decrease and our product concentration is going to increase, because that's going to give us more products and less reactants. It probably makes sense to say, because we're starting with some amount of it, it's going to decrease even more because we know we have this small Kc value. So again, we're going to choose the fact that we're going to say our BrCl decreased and our Cl2 and our Br2 increased to get to equilibrium because of the initial amounts that we have, because of the fact that we have this very small Kc value. And so now that we made that deduction, let's go ahead and follow through and see, did we make the right choice? So we'd have 0.250 plus x, 0.150 plus x, 0.100 minus 2x. So now again, we take this information, we plug it back into our Kc expression. So we'd have our Kc equals our BrCl squared, Br2 concentration, Cl2 concentration. And so now let's plug in the numbers we have. Our Kc value, 1.11 times 10 to the negative fourth, equals our BrCl concentration. So the expression we have for that, 0.100 minus 2x squared. And then we have 0.250 minus x, 0.150 minus x. I'm going to save us the joy of working through the algebra and just go ahead and say we've solved for our x value, and because we are going to see that we have x squareds that we're going to have included in our expressions, we're going to get two values for x. So let's see what those two values are. We would get x equals 0.0512, or our x equals 0.0486. And so we look at this and we realize both are actually positive. So we can't just always take a negative number and throw it out and assume that's the right choice, because here we don't have a negative number that we would say that doesn't make sense to use. So then we have to go back and again see, will any one of these give us a negative concentration? So for example here, if I were to take this expression here for our BrCl, if we take our BrCl concentration and we have 0.100 minus 2 times 0.0512, what we see here is that we would get a negative value as we're looking at this, because this is going to be something that is greater than 0.1, right? Specifically, we would see that we would get negative 0.0024 molarity. Well, we can't have a negative concentration at equilibrium, and so because of that, we'd say, well, that number does not make sense for us to choose as our change, and so we'd see, well, this is going to be our change here, because hopefully that's going to give us a positive concentration for each of our different species here. So now we'll go ahead, we're going to plug x into each of our equilibrium expressions. So we'd get a Br2 concentration of 0.250 plus 0.486. And so we'd get a concentration of 0.299 molarity. We'd have our Cl2 concentration again, 0.150 plus x, 0.0486. And again, those were the expressions that we originally set up here. And we're just plugging in our change that we found. So this would be 0.199 molarity. And then our BrCl concentration is going to be 0.1 minus 2 times our change. And again, that's because of the difference in the mole ratios that we have in our balanced equation. And so we would find that this would be 0.003 molarity. So now hopefully this gives us a chance to see the similarities and differences when we're trying to identify concentrations, whether we were given the initial concentrations of maybe two things, just our reactants, or everything, and we'd see how does that actually affect the process that we follow. It's the same process. We fill in our ice table, but in this ice table, what we notice is that maybe we have to think a little bit more about what we would write out as our change. And that's going to tell us something about what we would get for our final concentrations. So again, if you have questions on this, I'd love to answer those questions, but this helps us kind of work through the application of knowing Kc expressions and our Kc constant values.